talk with the questions and then
It's 10:30 to 11:30 or 10:30
yeah, it's 10:30 to 11:30, but sometimes it goes like 5, 10 minutes.
Finish 55 minutes.
Yeah, I mean, like we have the room until 12 anyway. Perfect. It has started. All right. All right. So thanks everyone for joining us today. I hope you all had a great week today. So for the first tea talk of the session, we have the pleasure to host Sarath, who is a prof here at Mila, and he'll share with us some thoughts on limitations of large language models. So before handing the mic over to you, Sarath, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, if you have a question, just like tell me you have a question. I'll give you the mic, wait for the mic so that people online can hear you, and then ask your question. For people online, you can just say in the chat, I have a question, and when time is right, I'll let you directly ask it. Of course, there'll also be some additional time at the end of the talk for people to ask further questions, make some comments, or have a more informal discussion with Sarath. For people online, please make sure you're muted during the talk and unmute yourself just when you have a question so that I don't have to manually mute you. That's pretty much it for me. So whenever you're ready, Sarath, the floor is yours.
Thank you, Ren. This works, right? Okay. Hello, everyone. Good morning. So I'll be talking about some of the limitations of large language models. I'm hoping that this talk would be a bit different than the usual hyping talks that you hear about language models. So the goal of this talk is really to show some of the fundamental limitations and like how we as researchers can improve upon these limitations, right? So before I get started, I want to give a very quick overview of the kind of research that is happening in my lab for students who are hearing me for the first time. So we work in three major areas in machine learning, which includes deep learning, reinforcement learning, and natural language processing. And most of our projects are in the intersection of these three areas, which used to be separate 5 years back, but now everything is merging together, which shows the progress that we have had in machine learning. And my long-term research vision is to develop interactive learning algorithms that continually learn from experiences. Okay, so which is the kind of guiding factor for most of the projects and publications that we have in our lab. So when I say interactive learning algorithms, it includes both systems like reinforcement learning, where you learn by interaction, but it's mostly reward based, and it also includes NLP, where you learn by interactions, but these are human language interactions, with systems and other agents, right? And we work on the core machinery behind these two kind of interactions, which is sequential modeling. And when I say continual learning, so this includes reinforcement learning and lifelong learning. Okay, so these are the major topics that we work on. But for today's talk, I'm going to just focus on some of the NLP projects, which are mainly towards the limitations of existing LLMs. Okay, so, well, I think we don't need motivation for why we talk about LLMs, especially at Mila, right? So we are a bunch of machine learning people who are in the forefront. However, this slide shows us that the size of the models has somehow exponentially increased over the last few years, right? So what was a small BERT model in 2017, now is a very big model like switch transformer or GPT-4, for which we don't even know the number of parameters, right? So typically these models are in the size of trillions right now, and it also has some effect on compute in the sense we need lots and lots of compute to train the next generation LLMs. Okay, here is just a snapshot of different LLMs that are out there. This is a snapshot from March 2023, right? So, and I'm sure there are 100 more LLMs to be added here. So people are releasing new models every week now. It's not even a annual or monthly thing, right? So we put so much effort as a community to just scale things and get better and better versions of LLMs, which comes with lots of compute, money, time, expertise, right? Now, you might have seen a lot of success stories of these language models. Like, so what I really wanted to do in this talk is to ask some of the fundamental questions, like, so where we still don't have a good answer, like with LLMs, even though a lot of people think that we have solved machine learning with LLMs, right? Like, so I'm going to ask a series of questions. Okay, so I did not give the complete outline here because I want to develop one after another. Like, so we'll start with the first question, which is, can LLMs consolidate world knowledge? Okay, or in other words, can they be good world models? Like, so can they integrate information like how humans really integrate information, right? So this is the first project, which is primarily done by my PhD students, Gabriel and Jerry. This project and several other projects that I'm going to show today are under review at EMNLP, and the anonymity policy prevents me from talking about them. But the results are due today, so I'm hoping that before this talk is released, like we will have the results, okay? So this work asks this question that can LLMs model the world, or can they consolidate the knowledge that exists in the world, right? So what do I mean by knowledge consolidation? Okay, so for example, let's say I train a model with a bunch of news articles, like there are some events happening on Monday, Tuesday, Wednesday, Thursday, etc. Right? Like, so I train a model with a bunch of news articles. Like, how does this model represent these news articles? Like, so these are related news, okay? And the question is, like, do these models represent these as just a bunch of like a distribution of facts or topics, or does it make sense by connecting things together and form a more deeper knowledge about what happened in that week, right? So this is the question that we were interested in. Now, how are we going to verify this, like, or validate like our hypothesis about whether they do this or not, right? Like, so here is a simple setup that we looked at in the paper. Like, so let's say I have a bunch of stories, okay? Now, I'm going to cut these stories into different parts, okay? And I have a bag of like parts of stories, okay? Now, I'm going to train two versions of these language models, like one which uses unsegmented stories, like which means the entire story is fed in one shot, okay? So while you do the pre-training, and the other part is like where I purposely split these stories so that the model has to somehow connect these things together, right? Like, so, and we are going to ask questions which require you to connect different parts of the story. Okay, so like, for example, like if I have this question from Harry Potter, like, so like we make sure that the answer for these questions, like to come up with the answer, you need to integrate multiple parts of the stories that you have seen in the training, and this is what I mean by knowledge consolidation. Okay, question? So the mic, like, okay.
Yeah, thanks. Just quick question for the segmentation, because they're books and they probably exceed whatever context window. How does that work?
Okay, I'm going to come to this. This was like a cartoon picture, so I'll show you the reality too. Okay, so of course, like we cannot feed the entire book into the current LLM's context window, right? Like, so we need like a different way of doing that. Like, so what we ended up doing is like, so we created thousands of short stories, like where, like, so this is an example, like, so where the stories typically fit the context window of the models that like we tested on, and like we trained one version of an LLM with the whole story fit into a context, and another version where like we just split the stories and put them in different batches and train these models, right? Like, so again, like, so we're going to ask questions which requires models to integrate all the information that they have obtained, right? Like, so now how does an unsegmented training model perform and a segmented training model perform, right? Like, this is what we are interested in. So here is an actual example, like from our experiments, like, so where you see the unsegmented model is able to answer the question correctly, okay, while The segmented model tries to make some answers, like, but it has a lot of, it misses a lot of facts, and it makes up things, and the final answer is wrong. Okay, so this is one example, but this really generalizes. Okay, so in the paper we also have results with OPT, but I'm just different scales of OPT, but I'm just going to show you like a couple of models here, just as an illustration, right? Like, so here we use T5 and the FLAN T5, which is the instruction tuned version of T5, just to see if this is the artifact of the pre-training objective or this extends to instruction tuned models too, right? So you see the light blue color, which is basically the performance of segmented trained models, models trained with segmentation, and dark blue is the one which is not trained with segmentation. Okay, so you see there is a big gap, like in performance, like which kind of highlights that these models cannot integrate knowledge from different parts of things that they encounter, right? Like, and what is interesting is like the hallucination rates of these two different models are significantly different. Like, so models which saw all the information together, they were able to model them together and remember them, and had lower hallucination rate. I think these are test hallucination rates. Like, training hallucination rate is close to 0 for all these models. Okay, so like it's much smaller when compared to like the hallucination rate for models which were trained with unsegmented stories. Okay, so in some sense this highlights like one of the potential reasons why hallucinations happen. Like, so hallucinations happen when you ask a complex question to the model where the answer for that question actually doesn't exist in one piece in the pre-training data. Okay, so like if you want models to really form knowledge which is different from distribution of facts, right? Like, so we don't think the current generation models can do that. Question? Okay, so these are like I have to check, probably few thousand to 10,000. Okay, so can you hear? Oh, good, for the online. Okay, I'll repeat the question for the online. So the question was like, how large are these training data sets, right? Like, so few thousand stories. I would argue not. I'll come to my argument soon. Okay. Okay. So why do LLMs struggle with knowledge consolidation, right? Like, so to answer your question, like our main hypothesis is that like it's really the training objective, like which doesn't encourage in any way like models to consolidate knowledge. Okay, because typically you train these models with the next word prediction, like, or masked language modeling, like whatever kind of LLMs that you are using, right? Now let's say there were two parts like of stories in the training set, like, so where there is one which says some celebrity is getting married in Miami next spring, and like there's another part which says hurricane hits Florida around the same time, right? Like, so now there is nothing in the training objective which forces the model to connect these two facts which seems irrelevant at the higher level, but they are connected in the sense like the hurricane is going to affect the wedding, right? Like, so these models might be good in connecting things that are seemingly relevant, right? Like, so that might be indirectly encouraged by this training objective, but I don't think they can put together things which looks irrelevant. And this is important if you care about AI for scientific discovery, right? Like, so we think a lot about how to create artificial scientists, like who can make discoveries. Like, to make discoveries, discoveries are not about connecting the knowns, right? Like, it's more about connecting the unknowns. Like, and there is no inbuilt capability in these models, like which really enables this kind of connections. Okay, can we solve this with scale? Like, so like if I just increase the number of parameters, like, so am I going to match the performance of these two settings? Like, most probably not, right? Like, so like even if you scale these models, like the objective is still local space. It's not based on connecting things from other places. Is that a question or a?
Irina, can you ask your question?
Yeah, so basically I was asking, are you sure this is scale independent property and scale? I'm not saying that scaling the model, but also scaling the data properly will not solve it.
Okay, so scaling the data, we are working on that right now. So one thing I want to highlight is like my student Gabriel, who is working on this project, he believes in scaling. So like he wants to make sure that like, so I don't believe in scaling that much, but he believes in scaling. So he wants to make sure that this is not something that can be solved. Okay.
I think it's important to scale also properly, and it's not necessarily just scaling the model size. You need to scale simultaneously data and model. Well, we can discuss offline, but I'd be happy to discuss that.
That's what we are working on right now.
Yeah,
we can talk more. Okay, so like just to summarize this discussion, right? Like, so like what we currently have is like what I would call as so what we currently have is what I would call as type 1 systems, like which are basically trying to set up a probability distribution over sentences or topics or facts, whatever you want to call it, right? Like, so if I show a model that Tom ate an apple, Tom ate a pear, and Bob ate an orange, like when I ask Tom ate dash, it's going to predict apple, pear, or orange with some probability distributions, right? Like, but what we really need for knowledge consolidation is a model which can, with 100% certainty, say that Tom ate an apple and a pear, right? So this is a fundamental limitation of probabilistic models that we develop. Like, so maybe there are ways to improve this, right? Like, but what I want to highlight is current generation LLMs are type 1 systems, like not type 2 systems. Okay. Well, I think that's what these cartoons also show. Like, so when you have a bunch of training corpus, these models are really putting together these training corpus as a distribution of facts. Okay, but what we really need for a good knowledge-based agent is something that connects these facts. Like, so knowledge is defined as connection of facts. Like, okay, so not just distribution of facts. One side note, like, I don't want you to be fooled by the like really good in-context learning capabilities of these models. Okay, so I did not talk about in-context learning at all here, right? Like, so like, because with in-context learning, you can do a lot of things, like you can connect things together in the forward pass, right? Like, but that is not the capability I'm talking here about. Like, so I'm talking about inherent knowledge consolidation capabilities, and these are complementary. Like, if you have a good knowledge consolidation agent, you can further improve its performance with in-context learning. Okay, so that's the first question. Like, so can LLMs consolidate knowledge? Like, the answer is no, right? Like, so now next I want to ask the practical next question, which is, I established that like they model a distribution of facts, right? Like, so now the next question is, do they use this distribution of facts that they are learning effectively when they do a downstream task, right? Like, so do they use the knowledge, like, but not by knowledge, I really mean facts here, right? Like, not the true knowledge. Can they use the distribution of facts that they have learned effectively while they are performing a task? Okay, so this is again another EMNLP submission, like, but we managed to put it in archive a month before, so you can read the paper after the talk. Like, so this is the work done by Amir Hossain, like one of Siva's students, with me, and like, we are going to take different LLMs and measure the knowledge utilization gap that exists in these LLMs. Okay, so again, like, so these models are trained with lots and lots of data, right? Like, so like, even though they cannot consolidate them, like, so they do learn some useful facts from these data. Like, for example, when I prompt a model with the capital of Francis, like, it's going to say Paris, like, and I can ask a bunch of other questions like this, right? Like, so, and typically these models like capture a lot of useful facts, right? Like, and we're going to call these as the acquired parametric knowledge of these models, okay? Because these models somehow capture all these knowledge in their weights, and when you ask questions, they're able to answer questions based on this knowledge, right? So now the focus of this project is like, we're going to check how much of this acquired parametric knowledge is really used in a downstream application. Okay, so of course it's going to depend on what kind of downstream application we are going to look at. Okay, so we will talk about that in detail. Okay, so we are basically questioning this common assumption that if the model possesses a certain type of knowledge, it utilizes it when performing downstream tasks related to that knowledge. Okay, so what do I mean by downstream task? I mean any fine-tuning task that you care about. Like, so you take a pre-trained model and you have a new task that you want to learn. Like, so you just do a downstream fine-tuning, right? Like, there are many ways to do that. Like, so you could do supervised fine-tuning, instruction tuning, like whatever method that you want, right? And let's see how much of this knowledge will get applied in downstream tasks. Okay, so this is how we are going to test this systematically. So we are going to first extract the model's parametric knowledge. Okay, then I'm going to create a downstream task which is tailored for these models' knowledge. Okay, so we know that this knowledge exists in the model, and I'm going to set up a task which requires the model to use this knowledge. Okay, and we are going to measure the knowledge utilization in these tasks. Okay, it's a bit tricky to do. Like, there are some caveats here and there, like, so we will talk about it. But this is how the setup works. Like, so we're going to take some diagnostic data set, which is a distribution of facts. Like, so it could be free base, like, or it could be any knowledge triples that you have access to. Okay, and I'm going to take a pre-trained model and first extract the model's parametric knowledge, which means I'm going to do soft prompting and figure out like what are the facts which already exist in the model, like that I can extract from the model, right? Like, so now, as you can see, this is not like an accurate process. Like, so I could miss facts because the prompting is not good enough, right? Like, but what is important is like at least these are the facts that we for sure know that exist in the model's parametric knowledge. Okay, so I'm going to take this particular data set, and let's call this as d theta, which is the data set created with models knowledge. And I'm going to set up a new downstream task. And this downstream task will look something like this. Like, so I'll take a fact from the model's knowledge and ask questions based on this, right? Like, so where did Barack Obama graduate from? And there are a bunch of answers here. So some of them are relevant, some of them are not relevant, like, and some of them are confusing, like, and there's only one right answer here. Okay, now we are going to take this downstream task data and split it into train and test. Okay, and I'm going to train my system to like do this fine-tuning, do this task. Basically, I'm going to fine-tune the models to do this task, and I'm going to test their performance in the test set. Okay, now the way in which we have set up these questions is that the only way the model can answer is by using the fact that it has in its knowledge. Okay, so now let's see how these models perform, right? Like, so as a first step, like, we're going to see how much of the encyclopedic knowledge that these models can actually recover. And this actually varies depending on the model that you use. Okay, so like, interestingly, BERT was able to acquire more facts from this particular like encyclopedic knowledge when compared to OPT. Like, okay, but I will also show you that OPT is actually better in using this knowledge a little bit when compared to BERT. Okay, so it really depends on the pre-training strategies, like the kind of data that you used, etc. Okay, so here you see that BERT, for example, roughly recovers 47% of the knowledge. Okay, so this means this 47% of the knowledge actually exists in the model's like memory or whatever you want to call it, right? And I'm going to take these like fraction, and I'm going to set up a downstream task, and we're going to check the knowledge utilization. So now you see that they don't utilize all the knowledge that they have, right? Like, so like they roughly utilize 80% of the knowledge, like 20% of the knowledge was not utilized. Okay, so, well, first of all, it might look impressive that they are using 80% of the knowledge, but I'm going to show you more results soon. Like, so this is like a really nice setting, like where like everything is ideal for the model to utilize its knowledge. Okay, so here I'm summarizing both those figures, right? Like, so what you see in the red color is the usable knowledge of the model, and what you see in the gray or like dark gray is the identifiable knowledge, but the model cannot use this. Okay, and this is something that the model. Okay, I think people in the remote cannot see my pointer, but the light gray is like the facts that the model was not able to. We were not able to extract from the knowledge of the model. Okay, so the gap 1 is the missing facts. Gap 2 is like the utilization gap. Okay, so ideally, like as we scale, we hope that these gaps shrink or disappear at some point, right? Like question.
Yeah,
I'll repeat it.
okay. Yeah. So I'm confused about. So the gray is things that you fed to the model, but you weren't able to get out as a prompt. Is that it? And then
Yes. Okay. So
this
is the part that I was able to extract from the knowledge of the model
by prompts.
by prompting. Out of that, it was able to use this portion in the task, in the downstream task.
Right. And so the unused part are things that were fed in the training data but were not.
Okay. So
What is the light gray?
okay. So the question is, what's the light gray? Like, so unused part. So not the unused. Like, so the light gray part is basically the facts in my knowledge triples that doesn't exist in the parametric knowledge of the model. So they are not from the training data per se, because we don't have access to the training data for these models, right? Like, so that doesn't say anything about how bad the model is. Like, so it's just that like this is the only set of facts that it could acquire, and we are also hoping that as you scale, that gray gap is going to reduce.
So question 1, maybe more of a comment. It does seem a little unfair that because we don't know what these models are trained on, to like compare them in the knowledge.
Yeah.
So
Yeah.
this is going to be in the training set.
Okay, that's good. Like, so the focus here is not really okay. The question is The question is it's unfair to compare these models. Like, I want to highlight the focus here is really not to compare and rank models. Okay.
Okay, my second question though, I'm concerned that you mentioned that in going from your usage, going from your identifiable to usable, you had a learning stage. And I'm concerned that you could just mess that learning up, overfit your data, and screw up generalization to your test set, right? So you can actually make this as arbitrarily low as you want based on your code.
Yes, so that's why the second question is like there is a learning involved for the downstream task, like, so there might be some issues with that, right? Like, but that is kind of going to be true in any downstream task. Again, to make this a little bit more fair, like, so I'm going to show you different OOD settings. Like, so basically we should just compare this with what happens in OOD settings. Okay, like they are both imperfect. Like, and we could make things.
Sure, maybe you can make me feel better by just telling me what was your stopping criteria.
Okay, so I think it's the validation performance. Okay, so like
On this task.
yes. Okay, but every stage has some issues. Okay, like, so, but like we are really not going to compare these models in the end. Like, we're just going to see a big picture with some grain of salt, of course, right? Like, so, okay, let's continue. So would scaling close these gaps, right? Like, so here we tried OPT, like different sizes of OPT, okay, and 2 versions of Llama that you could run in an academic setting, okay. But we are working on like having bigger ones, like if possible. So you see that this line increases, which means that the first gap is reducing as you scale. So the models acquire more and more facts, okay, like as you scale. But the gap between the acquired and usable knowledge, it just persists, okay. So like, so here you see the gap 1 is reducing, but the gap 2 is constant. Like, so there is nothing with scale which helps you to close the second gap, okay. Again, scaling, people could argue that like maybe we should do this better. Like, again, some caveats, okay. So what is really interesting is like, how would these models perform in a real downstream task, right? Like, which could be anything that you care about, right? Like, so again, to simulate that, like, so we set up like whatever I showed you until now, it's in distribution testing, okay. So we set up some out of distribution testing tasks, which are more close to the realistic scenarios that people use these models for, right? Like, so, and the accuracy on the downstream task like went down significantly like when we look at this out of distribution setup. Okay, so if you want to know how we set up the out of distribution setup, like so, like we basically took parts of the relations, like in the model's knowledge, and we did not use it in the training. Okay, so they only learn to do the task, but not like for all the relations, right? Like so now at the test time they have to generalize to relations that they have never done this task, right? Like so, and this significantly affects the performance of the model. Okay, so this kind of highlights that, like again the same story like the previous project. Okay, so like the models would perform well as long as you stay close to what they are trained for, right? Like so, but if you want to use them in downstream applications which are a bit different from what they were trained for, like so, they are going to struggle in using the knowledge that they have gained. Okay, so as a takeaway, right, like so these pre-trained language models exhibit two gaps: acquired gap knowledge and gap in acquired knowledge and gap in usable knowledge. Larger models only close the first gap, and distribution shift is going to harm the utilization further. Okay, so like what I want you to take away from this like whole project is just these messages. Okay, so not the comparison of different models, and of course we can improve everything that we have done here, like if we put so much thought on like each of these stages of this evaluation. Okay, so the answer is not always like so, like in nice settings they are going to use the knowledge that they have learned, but in more harder settings they are not going to use this knowledge. Okay, then the next question I want to ask is, like, can we use these LLMs as continual task solvers? Like so, like I think a lot about continual learning, like and like for me, like the obvious way to scale like the deployment of these models is to do continual learning, right? Like so, like let's say you have a trillion parameter model, you definitely don't want to fine tune this for each task separately and keep multiple copies of trillion parameter models, right? Like so, you want to deploy one model that can do many tasks, right? Like so, when you start doing one model that can do many tasks, where you don't have all the tasks available at the same time, continual learning is the only way to go, and it has the classical catastrophic forgetting issues, right? Like so, now the question is, can I just take these very large models and do continual learning? Is it going to solve the catastrophic issue for me magically, so that like I don't need to worry about continual learning, right? As you can guess, the answer is not yes. But let's see how to prove that, right? Like so this is work done by one of our summer interns, Sanket, with my PhD student Darshan, and like, well, it was recently published at JMLR 2023, but I should highlight that the work was really done in 2021, I guess. Like so it took us 2 years to go through the JMLR process. So whatever you see here, if it doesn't look new when compared to the other state-of-the-art findings, like it's because this was done in 2021. Okay, so the question that we ask here is, like, does pre-training help in alleviating catastrophic forgetting? Okay, so I want to show you like a comparison of two different models here. So these are two Distilbert models trained on a series of 5 tasks. Like what task doesn't really matter. Okay, so like it's a split Yahoo QA task. Okay, so but similar results would hold for different tasks that you consider. Okay, so the only difference between these two models, blue and red, is that I pre-trained, like I initialized the blue model with a pre-trained weight, and the red one is randomly initialized. Okay, as you can see, the average performance in all the 5 tasks like is significantly better for a pre-trained model when compared to like a model that is not pre-trained, right? Like in fact, it's not too bad. Like there's only 10% reduction, like in overall when compared to other models. So maybe we don't need to care about forgetting that much, right? So this is the motivation, right? Like so now we went on to do like more detailed study with different models and different algorithms. Okay, so this is like a very long paper which has significant like NLP experiments and computer vision experiments, but I'm only going to show the NLP part, even in that part of the NLP part that fits the story. Okay, so here you see like for 2 different data sets. Well, here I have the CV. Okay, so let's just focus on the NLP. Okay, so there is a 5 data set NLP task. Okay, where you see the comparison of pre-trained versus randomly initialized. So red is randomly initialized, violet or purple, that is pre-trained. Okay. So what is interesting is a pre-trained model, okay, which is just doing continual fine-tuning, like no specific lifelong learning technique incorporated into the algorithm, right, is already doing much better than like a randomly initialized model which uses EWC or experience replay. And experience replay is the state-of-the-art technique for solving catastrophic forgetting. Okay. And when you add these techniques to this pre-trained model, things get even better. Okay, so this is the accuracy, and here you see forgetting. So forgetting is lower the better, and you see that the pre-trained models forgetting is much lower than experience replay or supervised fine-tuning with randomly initialized models, right? Now, how do different pre-trained initializations affect forgetting, right? Like so here we compare, like again, like on the same 5 data set setting, like, but we are comparing different models like BERT, Robert, like etc. Like again, this was what we had in 2020. Okay, so these are like BERT, Rabata, DBERT models. Like so, some of them are fine-tuned, just fine-tuned. Some of them are like they added the experience replay capability. Okay, so what you can see here, like maybe it's not very clear from this figure, but I will summarize. Is interestingly, if you have diverse pre-training data, okay, then the performance of even a smaller model with diverse pre-training data is better than like a larger model which has less diverse pre-training data. Okay, so it's not just the size, but also the diversity of the data that matters. Like so, the better the diversity of the data, the larger the model size. We hope that it's going to act as a good initialization, and you start from there. Like you can do better than randomly initialized models. Okay, however, the forgetting is still going to be there, like if you move to harder tasks. Okay, so in this paper we also introduced a 15 data set NLP benchmark for continual learning, like where like you see that the performance keeps decreasing as you add more tasks. Okay, and this is also set up in such a way that there is a lot of variety in these tasks, like classification, generation, class imbalance, like big data size, like small data size, etc. Okay, so this is like a variety of tasks, and like when you have a variety of tasks like which are diverse enough, like the performance of even the pre-trained models reduces. Okay, so here you see the accuracy and forgetting, like and the results are similar. Okay, now why does pre-trained model have
Sorry, can I ask you a question? Yes. So learning accuracy here, I might have mentioned it. I'm assuming this is just accuracy on the training set or something.
Okay, no, so I skipped the learning accuracy for the start, but learning accuracy is like what plasticity people care about. Okay, so it's basically the accuracy on a particular task once you finish the task. So it's not about forgetting. So ideally we want systems which has higher accuracy, lower forgetting, and also higher learning accuracy.
That explains why there's not much difference.
Yeah. Okay, so why does pre-training help, right? Like so, like we have a bunch of analysis in the paper. Like there's just one thing that I want to highlight, which is like when you do pre-training, like so in the bottom you see with pre-training, in the top you see without pre-training. Okay, so when you do pre-training, like so, like the model is in a nice flatter region that you can reach these different tasks like in nearby settings. Okay, so like it puts you in a flatter region where it is easy to generalize to different tasks, like unlike like a without pre-training setting. Okay, and I think I will stop there like for this. Like so, like my answer for this is like yes, you can use them for continual learning. Okay, but CL is not solved. Like so, like you are going to have the same forgetting issues. Like so, I would like to think this as just a better initialization for the continual learning problem that you care about. Now you have the same challenges. Like so, you still need to think about like plasticity. You still need to think about forgetting. You still need to think about forward transfer, backward transfer, etc. Right? Okay. So now I'm going to switch gears, like and talk about like a few other challenges, like let's say we develop these bigger and bigger models. Like so, can we interpret the decisions that these models take? Right? Like so, this is really important if you are thinking about deploying these models in settings where they make decisions or they give actionable like items to humans who are making the decisions, right? Like so this is a work done by my PhD student Andreas. Like so this is again under review at EMLRP. This is a really interesting work where Andreas develops like a masked language model, like which is inherently faithfulness measurable. Okay, so I'm going to talk about what I mean by faithfulness measurable. Okay, but to motivate the problem, right? Like, so how do we measure? Like, how do we do interpretability in these LLMs? Like, so one of the most popular approaches for doing interpretability is like some sort of importance measure. Okay, let's say I have a question. The movie is like I have some sentence. The movie is good. I really liked it. Like you have an LLM which takes this and gives the sentiment. Okay, now what part of this like sentence made this model to say that this is a positive sentiment, right? Like, that is what I mean by like importance measure for each of these words, right? Like so, like you could say, okay, so these words contributed more when compared to things like the, is, etc., right? And there's also methods like leave one out, importance measure, where you try to mask certain thing and see if the model performs, like if the performance of the model varies, right? Like if the performance of the model varies significantly when you mask something, then that is one of the influence, like one of the like most influential words for making this decision, right? So we have a bunch of these like methods that people have developed in the last several years. Like, and if you want to learn more about interpretability for LLMs, like so, Andreas has like this really long but very, very useful survey which gives a complete map of different interpretability methods that people use for like understanding LLMs, right? Like, and this focuses on post hoc interpretability. Okay, so by post hoc interpretability, I mean you have a trained model. Now you want to interpret its decision after training, which is more reasonable than the intrinsic interpretable methods, like where you develop models which are intrinsically interpretable, right? However, one major question with either of these approaches, whether you do post hoc or intrinsically interpretable methods, is how can we be sure that the interpretations are correct? Like if my importance measure says that, oh, this is the most important word, what is the guarantee that the model thought this is the most important word, right? Like, so unfortunately, we don't have ground truths for any of these, which means we could get really fluent interpretations or explanations, like from either of these methods, okay? And they might even look plausible for humans, but that might not be how models like make decisions. Okay, so this is what I mean by faithfulness of these explanations. Like, are these explanations really faithful? Answer is no for most of these cases. Okay, so like we just need to, so it's like t-SNE, like where you visualize things and you see the clusters, you believe that there is a clustering in the model's representation, but if you look into the details of t-SNE, like you will know that like most of this is our own imagination, right? Like so the same story for explanations too. Okay, so there are a bunch of post hoc methods, intrinsic methods. They have their own advantages and disadvantages, right? Like so what we are interested in is, can we develop like some strategy so that I can make these explanations more faithful for the models that we care about? Okay, so what we are going to do is, in some sense, in between post hoc and intrinsic method. Okay, so it is a post hoc method in the sense like I can work with any pre-trained model. Like you give me a pre-trained model, llama, OPT, whatever. Okay, so you give me a pre-trained model, and I'm going to do something on the top of that to make it more faithful, like in terms of explanations. Okay, so we are making the model more faithful. That's where the intrinsic motivation comes in, right? Like so, it's a fusion of like post hoc and intrinsic interpretability, right? Like so, and we are going to focus just on masked language modeling. You can extend it to causal language modeling, right? Like, but that's a separate project. So we're going to focus on masked language modeling, and I'm going to develop a model which can actually do the task that I care about, but also give me explanations that are more faithful. Okay, so how do I do that? So it turns out that the answer is really, really simple, and you can add this to any task that you consider. Okay, so this is what we are going to do. We are going to take a pre-trained model, okay, and we are going to do masked fine-tuning. Okay, so what do I mean by masked fine-tuning? Like I'm going to take sentences And with 50% probability, I'm going to use them as such for the fine-tuning task. And with 50% probability, I'm going to mask words between 0 to 100%. Okay, so this masked fine-tuning, if done properly, would ensure that the model has seen the masking token during the training, which would avoid the out of distribution issues of masking token that's kind of bothering a lot of the interpretability methods that people have used in the past. Okay, so when you mask something and see the model's performance changes, is it because it's important, or it's because the model has not seen mask in that particular place and it looks out of distribution, right? Like, so people did not bother about this confounding factor, and like I think like Andreas's previous work showed that this is a confounding factor, and like you should think about it, right? Like, and here we are really trying to fix that problem. Okay, so you do this mask fine-tuning. Now here is the comparison of no masking method, which means the normal fine-tuning that people do. Okay, then there is a masking method, which means that you always mask. Okay, and the 50-50 technique that we are using, right? So this is 0% masked performance, which means I'm testing these models with no masking. This is the actual performance in the downstream task. I want this to be as high as possible. So you see that the masking, the 50-50 and no masking, they are good. If you always mask, it's a bad idea. Okay, so we don't lose by masking just 50%. And here you see the 100% masked performance, which means if I mask all the tokens, a sensible model to give me the majority class, not a random prediction. Okay, so the black lines you see are the majority class, and you see when you don't do any masking, there is a clear out of distribution issue. Those models give random performance, like which are not the majority baseline. Okay, so ideally we want to be good in both, and the only thing that is good in both is the 50-50 strategy. Okay, so this is the first step. The second step, if you want to be more rigorous, is to make sure that there is no out of distribution issues, right? Like, so we do that by using some statistical tests. Like, so I'm not going to explain the method here, but here you can see the plain fine-tuning versus mask fine-tuning. Okay, and every time something goes below the black dots, it means that there's an out of distribution issue. Okay, so you see that just by doing mask fine-tuning, you get better, like in bringing the masks in distribution. Okay, and finally, now you can take any faithfulness metric of your choice and use that with this particular model. Okay, and here you see in pink the random, like what happens if I just randomly mask things, right? Ideally, I want my masking to be more meaningful than random, so which means all the curves should be below the pink. And you see that we actually have some of these occlusion-based methods, like which are much below. The lower the better. Okay, so these models, like basically this fine-tuning makes these models much more like faithful in the kind of explanations that they are doing. Okay, so as a summary, like, so we do mask fine-tuning, then we do in-distribution validation, and finally we measure the faithfulness. Okay, so this is a really simple recipe if you want to do faithful explanations for masked language modeling. Now, how to do this for causal language modeling that people care a lot about, I think that's something that we will work in the future. Okay, so the answer here is yes, like for MLMs, like, but we need to do more work in make this possible for CLMs. Okay, and finally, I want to like talk about the bias that exists in these LLMs, right? Like, so like the more we use these LLMs in everyday applications, like it's more and more important that we talk about the bias that these models perpetuate and like how can we reduce them, right? Like, so like we have multiple projects in this direction, but I'm just going to show you one of them, like which is like the work done by Abdul, my PhD student, and my postdoc Gonzalo. So this is an archive, so you can read it, even though it's MLLP. And like, what do we do here? Like, so like again here, the goal is we have access to pre-trained models. Okay, so I cannot touch the pre-training part because these models require a lot of compute. How do I reduce the bias before I use them for the applications that I care about, right? So if that is the goal, like, so then probably some of these are out of scope, right? Like, so there are pre-processing methods for reducing the bias, which only the large companies should do when they pre-train these models. And there are also in-processing methods that you can use when you reduce, when you train your models or pre-train your models, right? Then there are intra-processing and post-processing, which are computationally efficient, and we can do it for any model. Okay, so what we are going to do is, like, we are going to do some intra-processing work. Like, we are going to take a pre-trained model and modify the weights or the architecture so that it becomes less biased. Okay, so this work is really based on this previous work, which showed that maximizing the entropy of attention decreases the bias. Okay, so here is an example, like, where you have the attention in colors, right? Like, so this model focuses too much on Xi, and when you maximize the entropy, that bias is like less, and hopefully the model is less biased, right? Like, so the paper has some results which shows that the models become less biased when you do this entropy maximization. Okay, but is it really true that you should always maximize entropy, like, for like reducing that bias, right? Like, so we have a counter example, like, where here, like, you see the model has some attention, like, which was not previously attending to heat. Okay, by doing maximization of the entropy, like, so you are also affecting examples like this, where you are starting to put emphasis on the gender words, like, if you don't want to put it, right? Like, so in some sense, like, what we really, well, in some cases, like minimizing, in this case, this is an example where minimizing is, or just not doing anything, is a good idea, right? Like, so essentially, like, we need entropy modulation, not minimization or maximization. Okay, so this is, again, like, the recipe is simple, it works. Okay, so that's the beauty, I guess. Like, so we have a really, really simple algorithm which takes any predefined model and then modulates the attention weight, like attention, by scaling the attention, like, with a validation set which is given for a specific bias that you care about. Okay, so however, when you do this, you need to make sure that the performance doesn't drop significantly. That's why it's important you compare fairness and performance, like, head to head, right? So if you see that there's always some sweet spot, like, where you have a little bit degradation in performance, but you have more improvement in terms of the bias, right? So here we compare EAT, which is our method, with a bunch of other methods, and you see that it has better demographic parity with slight drop in the accuracy, but when compared to the second best, which is random perturbation, like, there's a big drop in the accuracy. So random perturbation is not a good idea. Okay, and this is a method that you can combine with any other bias mitigation method. So when we combine like, EAT with any other methods, like, you see that it is really doing better in reducing the bias when compared to other methods. So I just want to show you a couple of very quick illustrations on, like, how EAT produces results, right? Like, so here you see the United Nations of Islam is an African American. Like, so this is the vanilla model, this is random perturbation, and this is the performance of EAT. Okay, so it tries to be less biased, like, so, and same is the case here as well. Okay, so again, it's a simple technique, not a lot of compute needed, right? Like, so you can take a model, do this attention modulation, you're going to get the benefit of reducing bias. Okay, so I will conclude with like, some thoughts on the current state of LLM research and the future challenges. Okay, so there are several risks that we have, like, with these models. Like, so misinformation is a serious problem, right? Like, so they hallucinate a lot, and there are a lot of people in the world who thinks whatever LLMs say is correct, right? Like, so and like, that's an issue. Biased information propagates very easily. There are privacy issues, right? Like, so we use the entire web data. We don't know how much confidential data that we are really using, which also brings the ethical issues, right? Like, so, like, can we use images generated by, like, someone else, like, without their permission, right? Like, so, and energy consumption, like, so companies are really running behind training bigger and bigger models, like, which requires a lot of energy, and also concentration of power, in the sense, like, only few companies can develop these models. If they're not releasing them, then, like, we have trouble, right? Also, I find ML as a field is stagnating with LLM. Like, everybody wants to do LLMs. Like, I have students who are working on other fields, and sometimes they have this fear of missing out, and they say, oh, maybe I should be doing LLMs, not reinforcement learning, example, right? Like, so this is not good. We are putting a lot of good minds into, like, just one particular problem, and it also deeply affects education. Okay, so, like, I consider myself as a teacher first, then researcher. Like, so, and I think this has a very deep impact in the educational system. Like some might argue that this is good, but I see a lot of bad things too. Like, so how I have a feeling that we might be training a next generation of people who are less intellectual than the current generation if we put so much emphasis on like the usage of these LLMs. Okay. However, to answer any of these questions, it is very, very important that we do open source research. Like, so if you don't do open source research and just use closed products, like, so like we are not going to address any of these issues. Okay. And there is one type of risk I did not put here, and I don't believe in it. Okay, so I want to highlight that LLMs are general purpose pre-trained initialization models. Okay, they are not AGI, as many people claim. If you treat them as initialization models, you can do a lot of innovative research in the academic setting. Like, so don't worry about you trying to pre-train or scale up things. Like, treat them as savior initialization or he initialization, right? Like, you have a really good initialization for the model. Now you think about what kind of problems you can solve with this not so randomly initialized model, right? So I want to quote my friend Shalar here, who said, if modern day LLMs are AGI, Google search achieved AGI 10 years ago. Okay, so, and if they're AGI, we would have solved reinforcement learning too. Like, we are not anywhere close to solving reinforcement learning. Okay, so these are really models which can fake the fluency, and yes, they are useful in certain restricted applications, right? Like, so coding or editing, etc. But they don't have agency. They are not going to take over the world. Okay, so here are some more technical future directions on the top of the risks that we should be thinking about, right? Like, so how do we design factually grounded LLMs? Like, so, like, one of the big missing pieces in LLMs, like if you really want to go to the AGI route, is memory. Like, so any intelligent agent should have good memory. LLMs have no memory other than the parametric knowledge and in context learning, right? So, like, machine learning as a field has not made much progress in memory augmented agents. Okay, so like I think that's an even bigger block of research that needs to be happen than scaling up LLMs. How to efficiently pre-train these methods, like, so that we can do this at academic scale, for example, right? Like, so I believe that in 5 years or 10 years, like, we will have much smaller models, like, so which can do the same things that bigger models can do. That's just because we figured out how to do these things properly. How to design updatable LLMs, like where you can update the knowledge of these LLM incrementally so that you don't pre-train again and again, right? That's important. Handling multiple modalities, like some progress is happening there. And well, as I said, like smaller models with same emergent capabilities is possible. I don't think these properties emerge at scale. Okay, so like if you do it properly, like, so you will have like really powerful small models, and I'm confident that we will figure it out in 10 years. Okay, so like we will not have 10 trillion parameter model in 10 years. We will have like probably a billion parameter model, which can still achieve the performance of 10 trillion parameter model. And finally, like I want to end with this like slide where I think we are close to AGI, but we are not. Like, so we have LLMs, like, but once you move past LLMs, like, so you're going to have even bigger challenges for machine learning research. Like, I foresee memory as one of the most important challenges that we haven't addressed. Like, but there are many, many more. Like, and we will keep on progressing. Okay, like, so, like, I really want people to not think too much about getting stuck in the LLM era. So this is a bunch of papers that I talked about today. I chose to talk mostly about unpublished work, so that because you can see the published work already like online, right? So I'll stop here and take a few questions. Thank you.
We have time for a few questions. We had one from Irina online.
Yeah.
So basically the point about reinforcement learning. So what do you think about like the DeepMind's other algorithm from like February and so on? So basically it doesn't have to be a language model, right? I mean, the fact that is kind of the very wide and scaled pre-training on large number of data sets or large number in case of reinforcement learning environments. is matched by kind of sufficiently capable model to incorporate information. I'll scale here again. Actually leads to kind of compositional generalization. So basically, it's not language necessarily, but say other. It's just one example. Is capable to adapt few short or nearly zero shot to kind of novel environments in the reinforcement learning setting. So just one example. So basically, it's like not language that matters. It's the core property of foundation models kind of absorbing this information, recombining, and hopefully compositional generalization.
So I talked about language models, but I think I can extend some of these arguments to general foundation models. Okay, so yes, we can do much better than the current state of RL by scaling up things like having very big model trained on multiple environments, etc. Right, but we will have similar fundamental issues there too, right? Like, so we don't, these agents don't have memory, and they might get really good in context learning. By the way, like, even though like I'm not like arguing for scaling, like I'm really impressed by the in context learning capabilities of these models, right? Like, so we could have really good in context oral agents, like, but for me that is still limited. Like, so if you want to move past beyond in context learning, like, so then you need to think about some of these problems that I talked about, like knowledge consolidation or memory, like or having agents that are really curious to go and figure out and seek more knowledge, right? Like, so those things I don't think are solved by
Memory augmented language and not just model. But yeah, I guess the question is like when people probably mean scaling and large models or large data, that also these days kind of covers aspects such as memory augmented and so on. So I guess it's more of a question of terminology.
Yeah. Okay. Yeah.
Thank you. So I've been working on like you're formulating it as in context learning, and another adjacent formulation is like retrieval augmented generation. Like, and from my experience over the last while working with this, they seem to work very well for a wide number of tasks that are quite broad. So, and just running these things in a loop with a very high level query, giving access to a variety of tools, and then letting it go seems to go and access the whatever store you have, if it's your documents or the internet or some other API, and then using that as a memory, loading the correct context in, and then being able to answer and solve like a variety of problems. Okay. And so this in comparison, like the dream of like, the neural Turing machine work and like that whole line of like being able to augment with parametric knowledge, this seems to have realized it in some really nice ways that don't require storing everything as parameters and like learning when to read and write and when to stop.
I agree with that. Well, first of all, it might be true that for most of the practical problems, like the common practical problems that we care about, just the current model within context learning is good enough. Okay, so like it really depends on the problems, right? Like, but when you talk about retrieval augmented models, right? Like if you retrieve information from the web, yes, then that is the memory. The entire web is the memory. Maybe that's a better neural Turing mission, right? But it doesn't solve the problems I'm talking about. Like, so you're really putting like all the work on the retrieval system, right? Like, so now the retrieval system can find relevant things, but can these retrieval systems also find seemingly irrelevant things and connect them together, right? If you have all the context, then in context learning is the solution, right? Like, so I give you all the pieces of information you want to do the task, in context learning can do it. But if the question is also figuring out what is the right context for the task, right? Then in context learning or retrieval augmented systems cannot do it, right? Like, so like you can solve it by working more on retrieval augmented systems. Like that's one way of making progress.
So just to parrot it back, I think what you're arguing is that, if you could integrate this sort of process into the actual training of the LLM, that likely you would get a better compression ratio or something along these lines, and you would identify things which seemed not to be connected, but are.
That is one of the ambitious goals of my student Gabriel, like, so who did the first project. So he's looking at how to like integrate this in the training part, right? Like, but then it's really, really challenging. It's not like training a simple model, like so, and we don't have compute to do these kind of things, right? Like so, but also it is not a trivial extension from the current pre-training to this kind of knowledge-oriented pre-training. Like I have a feeling that if you can solve that, you have solved AI. So like it's not easy. Yeah.
So yeah, I agree with you that like memory is like a huge issue, and we need to overcome that hurdle to really push LLMs to the next level, or any of these foundation models. But apart from that, like some of the other like fundamental problems you talked about regarding LLMs, like the knowledge gap, I guess building up of knowledge from the training set and all these things. I really feel like these are the things which seem to generally improve with scale of like, as you scale the data and the, the model itself. Like, GPT-4 is fairly capable of like, stitching together like random facts from the internet to like answer your question. It does make mistakes, but it is a lot better
But
than
I
like
don't want to think
GPT-3,
too much
right?
about GPT-4 if I don't know what the system is, right? Like, so you don't know if it is just a simple neural network. Like maybe there's a whole stack on top of the neural network, which does all these things in a hard-coded fashion, right? So
Okay,
let's not talk about GPT-4.
fine. Maybe Chat GPT, because we're fairly certain that's just GPT 3.5 with,
Well, I don't
knowledge.
want to think too much about any of these OpenAI models, like if they are not public, okay? So like, because these are not models, these are products. Like, so you don't know what is the wrapper between GPT and you. So like, we should not fool ourselves with these products, okay? So like, on the other hand, if you look at open models where you know that this is just a model, there's nothing on the top of that, right? Like, so I think, so then these issues still persist.
Okay, I guess the main point is, like you seem to, like what you said is that, the scale may not be the most critical thing, and we may be able to, distill these models down to like, to be much smaller, which might be true. But at least as of now, the trend we see is like, things like in context learning, which, you admit is like, really powerful tool, right? Is something that seems to emerge with scale, and a lot of these other, abilities do emerge with scale.
Yes, but what I say, or what I hypothesize is like these things can be possible with smaller models too. We haven't figured it out. We will figure it out, right? Like so, and like we already see progress in the opposite direction, right? Like just in the last few months, there are like multiple billion parameter models introduced, which matches 7 billion or 30 billion parameter models. Like, and this trend will only get stronger in the next few years. So,
Okay.
Andreas?
There's somebody online who can ask that question.
Oh, yes. Hello, do you hear me?
Yeah.
Yes, thanks for the great talk, first off. I was wondering what your thoughts were on like reasoning in LLMs. So usually, like we see it able to reason and do so out of distribution in like an increasing like a fashion with scale. And I feel like some people argue that at some point you don't need to actually reason properly if you can just simulate reasoning like better and better. Like, what are your thoughts on that versus reasoning and like LLM's capacity to do that?
Well, in context learning does some reasoning, right? Like maybe it does like really good reasoning, like it might be the state of the art reasoning method, right? Like, but if you don't do in context learning, like if you just ask a question without any context, like can they really internally reason and answer these questions? Like most definitely no, right now, right? Like so it depends on what you care about. And about faking reasoning, like I think I'm forgetting the name of this book. There's a very nice book which argues that reasoning is all like artificial and human made. Okay, so like when we reason, we are really trying to convince ourselves on the decision that we have already taken. So in that sense, reasoning is always approximate, right? Like, so yes, you can fake reasoning, and in fact, that is what these methods are doing. Like, and they are doing that by simulating what exists in the data, right? Like, so humans try to fake a lot of things, and those things exist in the text that we see in the web, right? Like, so if you simulate human, okay, so they're really trying to simulate human through the web data. And I think some of the current work that Andreas is working on, like, so is trying to prove that, like, even though people think language models are good causal reasoning mechanisms, like, so maybe they are not truly doing causal reasoning. Like, they are trying to fake causal reasoning from the data, but they don't understand like how to do it properly. Okay, so most of these reasonings, yes, they can be faked, and yes, they maybe faking is enough for practical purposes. So, question?
Okay, so it seemed like one of your strongest argument for why LLMs are dumb is they lack knowledge consolidation. Can you explain to me what is the difference between knowledge consolidation and compositionality? Because compositionality seems to have been pretty much solved or extremely improved by skill and a lot of training.
Compositionality is some sort of knowledge consolidation, okay? But who gives you these pieces to compose? Like, so if that comes from the context, then knowledge consolidation is not solved, right? Like, so, like, are they really putting together pieces from the training data? Well, Aaron would know more about compositionality, like, so, but I don't think they really put together things from the training data, like, unless you train them to explicitly train them to do so. So one interesting thing about all the projects that I presented today is, like, so you can take these limitations and make that part of your training strategy, right? Like, so you could train the models to consolidate knowledge. You could train the model to utilize their knowledge in irrelevant parts, etc. Right? Like, so you could solve these issues by posing them as training of your model. But I don't think. Yes, compositionality is related, but I don't think they can compose at the level that we think is required for knowledge consolidation. Again, like, in terms of in-context learning, compositionality is, I don't know, maybe solved. Like, so, like, you might compose things much better than other methods if you do in-context learning. Like, so without in-context learning, I'm not sure.
I had this thought during the talk when you were talking about memory. So if I talk with someone or think about something and then I'm like, oh, I'm forgetting this thing, what do, right? You go check on Google. And so I wonder, like, is there really a difference between what the LLMs like memorize and then the tool use they could do? Or is there something more to it? You know, it's like,
well, the difference is you know what to search for.
Yeah.
Right? Like, so, like
what's the
maybe
gap?
LLMs know a little bit about it, but I'm arguing that they don't know what they're looking for.
Yeah, interesting. So that may be the gap between.
If you can fix that gap, then yes, knowledge, web is your knowledge and memory, and you can do whatever you want with that, right? Yeah.
Yeah, you can follow.
My question is about different types of knowledge. So I think in your talk, you talk about like knowledge consolidation, and it seems to be like explicit facts and sort of combining them. Have you looked into other forms of knowledge, like more implicit, more procedural kind of knowledge, skills, these kind of things?
No, we haven't explored those in these projects. Like, but probably, like, if you work with foundation models for oral, then you can talk about skills and what kind of skills they learn, etc. Right? But yes, I agree there are other forms of knowledge. But given that these are with LLMs, like, so we were mostly focusing on facts.
All right, so we'll officially end the talk now. Thanks very much, Sarath. Again, thank you again. And thanks everyone for coming. Next week we'll have